Hi, welcome to Unit 6.4 Kinetics. This is part 1 of 2, where we'll be answering the key question, what are the factors that influence reaction rates? So we've already reviewed this in Kinetics video 6.1, so let's take a moment to sort of think about what we know. So I'm going to ask you a series of questions, and what you're going to do is you're going to circle the correct answer. So the first question. Which reaction would be faster, using 1 gram of mossy zinc or zinc chunks? So here are the zinc chunks, and here is the mossy zinc. Circle your answer, and then after that, I want you to see if you can come up with an explanation of why. Great, if you said mossy zinc, you would be correct. So the reason why mossy zinc is would make the reaction faster is that's because it has a greater surface area. Next question, which would be faster? So here we have a reaction with yellow dye, so that's shown here. And if you add bleach to it, it yields a colorless product. So would it be faster if we use 0.18 molar bleach or 0.09 molar bleach? Make sure you circle your answer. Great, 0.18 molar bleach because it has a higher concentration. Which reaction would be faster? Going from raw eggs to fried eggs using a high or low temperature? Right, high temperature would be a faster reaction. And that's sort of the reason why sometimes if we are cooking and we're getting impatient, we turn up the heat because we know that that will help the cooking process. So higher temperature, higher reaction, or faster reaction. Last one, which would be faster? Breaking starches down into sugars, in water, or in your mouth? Make sure you circle the answer. Great, in your mouth. And that's because your saliva has enzymes, which are biological catalysts, that sort of help break down starches and other carbohydrates. So what we just reviewed here are the 4 controllable factors that affect reaction rate: surface area, concentration, temperature, and presence or absence of a catalyst. And although we may intuitively kind of know these things, we're going to learn why using something called collision theory, which explains these factors. So what is collision theory? You may recall that during a chemical reaction, bonds in the reactant are broken, and then new ones are sort of reformed to make the product. And according to this collision theory, bonds are broken and reformed when particles collide into one another. So they actually have to crash into one another in order for you to break and make bonds. Now, the other part of collision theory states that only collisions that meet the following criteria will result in products. So 1, they have to have sufficient kinetic energy. And 2, they have to collide in the correct orientation. So as they're colliding, they have to collide in the correct way or with the correct placement in order for it to result in product. So let's take a visual of that. Here we have carbon dioxide and oxygen's going to crash into it. So let's say that this is a collision that meets the criteria. It has sufficient enough energy, kinetic energy, and it's the correct orientation. So that will result in product. Now let's break that down a little bit further. Let's talk about, first of all, correct kinetic energy. So here, this has sufficient kinetic energy, and these whooshy lines sort of are showing the speed at which the particles are traveling. So they're traveling faster here, and here not so fast. So this one's not fast enough to result in product. So remember, they have to have enough kinetic energy. And the higher the temperature of the system, the more particles will have that sufficient kinetic energy. So therefore, by increasing the temperature, you increase the amount of particles that have sufficient kinetic energy, thereby increasing the rate. The next one is orientation. So in the reaction above, we see the correct orientation is where the carbon in carbon monoxide collides with an oxygen in molecular oxygen. Here we have a collision that doesn't match that. So it's the oxygen in carbon monoxide colliding with another oxygen in molecular oxygen. That's an incorrect collision, so that's not going to result in product. So remember, we said they have to have the correct orientation. And there are several ways that we can increase particles having the correct orientation. The first thing we're going to look at is by increasing the frequency or the number of collisions. Because by increasing the frequency or number of collisions, you just have a greater chance of the collisions having the correct orientation. So things that increase the frequency of collisions, temperature, increasing the surface area, and increasing concentration. All of those will increase the frequency, thereby increasing the chance of correct orientation. Catalysts also can help do that as well. And that's because catalysts will sometimes hold particles. Some catalysts will hold a particle in the correct orientation, or they may provide a pathway to a more accessible orientation. So in either case, when it comes down to correct orientation, there's a lot of ways of getting there, either by increasing the frequency of collisions or by fixing it with a catalyst to make sure the correct orientation is reached. All right, so now that we sort of looked at this whole theory behind collision theory, we're now going to take a look at reaction profiles. And the reason why we do that is because reaction profiles kind of give us a sense of how much Ke and how much entropy is sort of required to get to that effective collision. And that's because in a reaction profile, there's several important parts. We know the reactant and the product, because we've seen these before when we looked at thermodynamics. But in kinetics, the thing that we look at is the transition state. And the transition state in this reaction between carbon monoxide and nitrogen dioxide is this transition state here, where the carbon monoxide carbon is colliding with the correct orientation with the nitrogen dioxide oxygen. And what you may notice is that in order to go from this reactant to this transition state, it requires energy. And that energy is known as the activation energy. So it's energy required to go from the reactant to the transition state. The higher that energy is, the slower the reaction, because that means that fewer particles are going to have the correct kinetic energy or be able to reach that correct orientation. The other thing that you may remember from these reaction profiles is how to measure the delta H, which is the change in enthalpy. And that sometimes will come up sometimes in questions that involve reaction profiles. You have to identify EA and delta H. So I'm just putting that here, even though that's really a part of thermodynamics. All right, now that we looked at reaction profiles, let's look at reaction profiles as it relates to mechanisms and intermediates. So here we have two reaction profiles. What do you notice is different between them? Right, so one thing you may notice is that in the first reaction profile, there's only one peak, and in the second, there are two peaks. So what does all that mean? Let's talk about that. Remember, each peak represents a transition state. And the number of steps in a reaction mechanism corresponds to the number of peaks. So here, this would be a one-step mechanism because there's only one peak. And here you have one two-step mechanism because there are two peaks. The next thing, the intermediates can be found in the valleys. So that means those are sort of the dips in between peaks. So in this second reaction profile, the intermediate is here. Finally, what we mentioned before, the larger the activation energy, the slower the step. So remember when we talked about mechanisms before, we had fast steps and we had slow steps. You can tell from a profile which one's the slow step, and that's by measuring the activation energy. So in the first profile, there's only one step, so we don't have to worry about fast or slow steps. So let's focus on the second one here where there are two steps, 1, 2. Now, we know to measure the activation energy when we go from reactant to our first transition state, it's just that energy from the reactant to that top of the peak there. But what about for the second step? Do we measure the activation energy from the reactant to the top of that peak or from the intermediate to the top of the peak? It turns out it's from the intermediate to the top of the peak. And why is that? That's because we already have enough energy at this point when we're at this intermediate. We don't have to go back down to the energy of the reactant. So now we're in order to go from here, from this intermediate to the product, we need to get over this hump. We don't need to go back down to the reactants. All right, so that's how we measure the activation energy from either from reactants to the transition state, or if you're dealing with an intermediate, from an intermediate to the transition state. Okay, so this sort of just summarizes. This is a one-step reaction profile, and here we have a two-step reaction profile. And now going back to our question of which step is the slowest and which step is the fastest, the first step is the slowest, and that's because it has a larger activation energy. You can see that's black double arrow here is a lot larger than this red arrow here. So first step is the slowest, second step is the fastest here. All right, now let's test your understanding of reading reaction profiles through the CFU. Based on the following reaction profile, how many steps and intermediates are formed in the reaction? Pause the video now, and when you press play again, the answer will be revealed. Great, so the answer is there are 3 steps. Remember, we just count the number of peaks, 1, 2, 3. And the intermediates are B and C because those are the sort of in the valley positions between reactants and products. Next CFU, which step is the fastest? And I want you to explain your reaction, your answer. That's spelled incorrectly. That should be AIN. And then is the reaction endothermic or exothermic? Pause the video now, and when you press play again, the answer will be revealed. Great, so the third step is the fastest, and that's because it has the smallest activation energy. You can see here, this activation energy is measured, it's pretty small compared to the rest. And then the last one, the reaction is endothermic. So we can measure the delta H, the difference in energy from the reactants to product. And you can see here the delta H will be positive because as we go from reactant to product, we're gaining energy. So this is endothermic because delta H is greater than 0. All right, that's it for video 1. Have a quality day. Oh,